So if you want to open up the portal, you can find all the content there, nice and organized for you. And so today we are going to look at this notebook if you open up the reward model. But before I do that, I just want to jump back to the overview and highlight this diagram again, just to give context to where we are. So we did step one. Step one was collect demonstration data and train a supervised policy. We're starting with a pre-trained GPT model, GPT 3.5 in the case of ChatGPT. We use GPT 2 because it's smaller and we didn't get hands-on, easy to train and get some initial nice curves at least, even forms and great overall. And then fine-tune that on examples of prompt response pairs and try and model that kind of language. So it should hopefully help the bot to predict things which are much more chatbot looking, right? Because every time it's going to make predictions, it will have updated those parameters such that those words come up more likely. And that left us with our supervised fine-tuned model down there on the bottom left. That was the starting point. It's a language model specialized to the domain of chatbot-like conversation. However, it still seems to have a lot of problems. It can do things like, give you very short responses or give you inappropriate responses. And it seems, even though once trained, these things can much better model the chatbot style interactions, they still fall off with things like behaving ethically, not doing inappropriate things, being safe, and such. And so the next two steps, step 2 and step 3, which kind of together really make up the reinforcement learning with human feedback, they seem to be the key to getting systems like this to really work. And so that's the jump towards much more natural models to interact with, is step 2 and step 3. So I didn't highlight enough yesterday, but they've really come together, because the point of step 2 is to end up with this reward model. But why do we need a reward model? We need a reward model to do the reinforcement learning, because in the reinforcement learning setup, you basically have some system interacting with the chat interface, and it gets a reward per response. So the reward model is what we're going to use there to generate the reward. We'll look into that tomorrow. But today, we've got to get this reward model. So the steps there, what are they? Well, we've got a single prompt and several different responses. And then you get a human labeler to rank them in order. They tell you which one they prefer most, which one they prefer least, and the order in between. And then you can, as we'll see, use that data to train this reward. So it's going to output a scalar value, a score of the reward for every prompt response pair. And if I do that for same prompt, different responses, I'll be able to score each of them individually, and the model should be able to tell me which one's better when I rank those final output scores. And so at the end of that, you have this reward model, and the point of the reward model is to encode the things which are very hard to write down the rules for. Things like I said, what does it mean to be ethical? What does it mean to be unbiased? What does it mean to behave in the kind of ways that you want this bot to work with, so that it's very pleasant to use and as helpful as possible? What does it mean to be helpful, right? Those things are hard to write down the rules for. It's easy to do language modeling, but it seems like this reward model is the step that's necessary to model those kind of behaviors that you want. So we have lots of human labelers, write responses which align with those things. So as a human, it's very easy to say this is like a helpful thing to do. That's an unhelpful thing to do. This is me acting professionally. This is unprofessional. It's easy for them to model that behavior well, even if they can't write down the exact rules for it. So that's what we hope to capture in the reward model. And then in the third step, what we're going to do is have the fine-tuned model generate new responses to some different prompts, and then those responses go through the reward model, and at the end of the day, you get a score for each response, and that should basically tell you how preferred is this response, and because of the way that we're scoring preferred as based on the reward model, that should basically be is it nice and friendly and helpful and ethical and safe and such. And then we'll use those rewards to update the parameters of the model in set 3. Does anyone want to run over any of that or any questions about that whole end-to-end system? Cool. Okay, so Amelia, can you talk me through like what was the what did we do yesterday in step 1? How did we do that supervised fine tuning? Create the data set. What was in the data set? Yeah, so we had few shot prompts and plain prompts. But we didn't just have prompts in the data set. We also had. Yeah, so we had the responses as well. So we need both those things. And then what do we do with that? Yep, got it in the dictionary. And then trained GPT using that data set. Yes, exactly. Which GPT did we use? Yes, that's right. Anybody remember how big GPT-2 is? How many parameters? 1.5 billion. Sorry, I lost who said that. But yes, that's correct. 1.5 billion parameters is a lot of parameters. How close is that to GPT-3? Very far. How much bigger is GPT-3? 175. Yeah, 175. So a lot bigger. So we're working with a little baby model on the left-hand side. Cool, great. So any other questions about that? Let's jump into it then. So yeah, open up the reward model notebook, and I'll talk through this this reward system. And I want to try and just, again, I keep saying it, but I want to try and do a lot more code today. And I've got some challenges at the end of this we can try and do if we get through all the material. So reward model does this, right? Just to put it plain and simple, reward model, it takes in the prompt and the response, and it gives you a number. The number is like, how good is this prompt? How good is this response to this prompt? And to do that, yeah, we basically need to get that ranking data set, which I showed you guys. So to talk through, to show that data, let me show that. I think I'm going to need to share that with you guys. So hold up. So I've got this reward data set. I decided that we can skip past this bit. It's wow, it looks like a huge mess there, right? But what's happening here, if I view it nicely, I've got different columns. The first column is the prompt, and then I've got different columns which are 3 responses for each of them: the least preferable response, the somewhat preferable response, and the most preferable response. So from this, how would I turn that into a ranking data set? If I want to basically have a model, or how would I turn that into the right format for my reward model to predict a score from? Just imagine you just started with this data. I know I haven't given you much detail yet, but what do you think the next steps are? What would you do with the ordered dictionary? But that's kind of the format it's already in, right? It's like, what we want to get towards is like, if we go through the data set, you know, we're going to run through that data set for an epoch, do that for many epochs, and every time I ask for an example, I should just be getting a prompt and a response. So that's what the reward model wants, right? And out of that, it's going to give us a score. And I'll show you a loss function after, which is going to figure out, okay, whether it's predicted scores in the right order. So what do you think my data set would look like? If my data set has to take in this data and then turn it into those response pairs. Exactly. Yeah, that's exactly what I'm looking for. Great work. Good stuff. So yeah, basically want to turn these 3 different columns, least preferable, somewhat preferable, most preferable responses, into every permutation of pairs with this prompt. So I should have one pair which is prompt, least preferable, another pair which is prompt, somewhat preferable, another pair which is prompt, most preferable. And that'll give me 3 different pairs per example in this case, or per ranking task, you could say. Each of these represents a task completed by a labeler. And once you got that, you just pass it through the reward model, right? We'll have an initially somewhat random reward model, but it should be able to get us a number, and then we can optimize that. Okay? So I will I'll go ahead and try and code that up with you guys now. There's some extra details in this section here if you want to read it. But let's do the data set first, and then we'll come back to the loss function. So I've got a solution there. I'm not going to look at it. I'm going to try and just copy the boilerplate of it and code that up alongside you guys. So pass there, and then I've got my classic reward data set, which needs to have a few methods implemented, which we'll get to later. So create the response pairs. Firstly, how do I read something in if it's in a CSV format? Can anybody help me with that? Let's fire through this. I know some of you guys know it. Look at my imports. Why have I imported certain things? I like it. Yeah, let me get the data. Which one is it exactly? 1 second, let me just find this. Okay, cool. Yeah. So I'm gonna upload from here. I've got this reward data set. I've just hit that button in Colab. I'm gonna open this up in there. And I don't know if I can't preview that in here, can I? But I'll also drop that into Discord for you guys now as well. So you'll need to upload that. And then we'll check our line works correctly. So I'm here in the Oxford General. I'll do that. Okay, so you should be able to find the reward data set in there now. It's just this CSV. And then you should be able to follow along exactly as I'm doing this. So I've got my reward data set there. So that's the CSV I want to read, obviously. Reward dataset.csv. I'll call that data. Okay. Nice. So let's print that first and call this function. It's got an issue here. There's something gone wrong. Okay. So I need to update that. Sorry, guys. What's happened there? Oh, yes. Okay. Cool. So it says I got an error on line 13. This is exactly the kind of problem you might face in the wild, right? I'm trying to read in my data. It doesn't like it for some reason. If I look at line 13 in my data set, it looks like this. What's the problem with this line? Can you say that again? Yes, there are commas in this line, and that is exactly what pd.readcsv is trying to separate on. So it seems like it's saying, hey, expected there just to be one field in here, but I got 3 because there were 3 commas probably there. Spinach, banana, almond milk, something like that. So how do I change that? If you look at this file, what is the actual delimiter which separates different columns? The line. Yeah, a few people know what it's called. Anybody know? It's a pipe. Yeah, it's a pipe. So how do I set this? Anybody know off the top of their head? I don't expect you to know. I didn't know, so let's just look it up. So pd read CSV. This is what I'm using. There should be some indication of in this call sign here of like, how do I specify how things are separated? Well, this one here says delimiter to use, and then it says some more detail, but basically this is the one. So it defaults to a comma. It's very small. Don't hesitate to say if it's too small to read, but it defaults to a comma. So what I actually want to do is separate that with a different value. So I'm going to say sep equals this pipe. If I run that, what happens now? Now it looks like that. So that's a lot better. That's a lot better. It's got this line over here though, which I don't really need. It's just the index column. So I think I can do ignore index. It's a little bit nicer. I know I've done that wrong. What am I trying to do here? Index column. I'm gonna do my example. All right, so we can do that once we got the data frame, but don't worry about it for now. All right, so we'll go with that. Data set looks like that. That's kind of nice. And now I basically want to go through and hopefully get every possible pair. So if I print data.columns, you can see all the different columns. Here they are. So I've got these 4 columns, and I basically want to come up with every pair of different responses which I can compare to one another, basically. So let's stay with a simpler case actually. So what I mentioned before is like I just want to pass in prompts and responses. How would I do that from here? I've got this pandas data frame data. It's like a table, and I can ask it for different columns. Welcome. Yes or no? You got your hand up. All right. To the pathway. Message Ahmad Alalti, and he'll give you access, or I can do it in a second. Okay, so how would I do this, right? Let's at least get to the point where I can, from this, return a prompt and a response, like that, okay? Somebody help me out with this. You've done a lot of Python so far. Should be able to get hands on with this. What do Hammersley's reckon? We're just going to return one at a time. Sorry. Yeah, so this that says create response pairs. I'm probably want to return a whole list. You're totally right, actually. So I'm going to say prompt response pairs is equal to an empty list. And then basically, as I go through, I want to append one prompt and a response pair to it, like that. So I'm going to add to that my pair. My pair is going to look something like this. So how do I get those two things? Yeah, I could do for row in data. Maybe it looks right, but when we run this, we'll see it does something slightly different. But yeah, roughly. Given the row, how do I get the prompt and the response? Not data, but now we've got the row. Yeah, so we want to get from the row, we want to get the prompt and the response, don't we? So if we look at the columns that we had prompt, and then we've got these three different things. So of course I want the prompt like that. And then I want to get all of the other ones as well. So let's just take those as a list. Let's say keys. They're the keys to my different column. So I've got that list of things, and then I want to do what with those to get all the different prompt response pairs. I'll give you a clue. That's the clue. Yeah, loop over those. How to do that, Payson? Index the row, yep. With the key, exactly, yeah, fantastic. So that's nice. So that'll get me each response one at a time, basically. That'll be pretty nice. So prompt response pairs should be filled up from there. And yeah, let's just take a look at what comes out of that. Well, let's try and run this. Always try and run it as quickly as you can. And then you'll see if there's any errors. There's a yellow line here. What's that about? Prompt response pairs is not defined. Spelling mistake. So if I run this now, I think I'm going to get an issue. And it says string indices must be integers. What's the issue here? What is this? Might not be obvious straight away, but I don't know what it is off the top of my head, but it's happening on this line, right? I see a lot of people leaning. If this is not big enough, you only have to let me know. So I see this, I see it's happening on this line, prompt equals row, prompt, what's happening there? How could I find out why is there an issue there? It's probably not a dictionary as we expect, yeah. Makes sense, this line, but it's probably not what it's returning us. So let's take a look at what it is, right? That's the debugging 101, print the prompt, or sorry, print the row there, and then we'll get an idea of what it actually looks like. And it probably doesn't look like what we think. It's okay, it's just the word prompt, right? So if we iterate through these rows or iterate through the data, it doesn't give us the row. It gives us the column names, annoyingly. So what we were expecting there is that essentially data is a list of dictionaries. But when you read in something with pandas, it comes out in this funny pandas data frame format, which doesn't behave in the same way. But there is a way to get it like that, which is to do data data.toDict. Doesn't actually turn it into a dictionary if you give it the keyword records. Sorry, if you give the value records for the keyword orient. So if you orient that as records, what that means is it will turn it into a list of dictionaries. So if I run that, things, okay, seems to be behaving much more like we expect now, right? So each row is at least a prompt response pair. Oh, sorry, a prompt and all of these keys pair. But then I got an issue which says this thing doesn't exist because I've given it the wrong name as well. And now when I do that, you can see what comes out the other end, right? So I've got these different pairs of prompt and responses. Cool. That's just warm up. Any questions about that, pandas? Practical stuff, getting your data out of the file and into the format that you want. But this is kind of a little step towards making the data set in the format that we need it to be, okay? Take a moment to do that, run over it. This isn't the exact outcome we want. We'll look at the next cell in a second. If you want to look ahead, feel free. That's basically what we want to feed into the reward model, isn't it? Yes, so what we're actually going to do, we're going to have data set give us one prompt and several responses. We put it in the model called contact and the problem was to get to the words. So in each example, we have to response compare that to the option one.
Yesterday, each one had a cost and one response, and then use the most so it is
Because we're going to use it as a loss function basically compared to because the thing is, right? You don't know what the right one is. You don't have that number. You only know which one better. That's by ranking by the label and just in yeah, so that's the all right, cool. So a good little thing to note there is that what folder is this? It's very tempting to click this button, and then you end up looking at all these folders. Oh, sorry, it's very tempting to click this button is the one actually, and then you end up with all of these. This isn't the folder above. So if you've done that, content, that's like the working directory. That's where you want to upload the data set, okay? But ideally you haven't clicked that button and you're already in the content folder. But I don't know how you get back in there now. So that's where it needs to be. Okay, I'm going to put up a complicated equation. I'm going to talk around it, and then we'll get into exactly what it means. But the key thing to notice, right, is that we want to train the model to predict the correct reward. It's a regression problem, predicting a continuous number. What should the reward be for every example? Remember the data that we have, right? It's just people have ranked responses in the right order. So we don't know what the actual label for the correct reward is. It's not the actual absolute value of the reward that's important. It's just the relative values. So we don't know exactly what the reward should be, so we can't optimize against it, but we can say, okay, if I've got 2 responses and a reward for each of them, the one which is ranked higher should have a higher reward, and the one which is ranked lower should have a lower reward. And that is why we use a different loss function. This is a loss function which looks rather complicated, but all it's doing really is comparing 2 rewards. So I've got the reward for the preferred response and the reward for the less preferred response. And I'm basically taking the difference between those 2. Obviously, the preferred response should have a higher reward, so it should be bigger. So if the model's doing well, this thing should be bigger than 1. Oh, sorry, bigger than 0. It should be bigger than 0. And then if we pass it through a softmax function, sorry, a sigmoid function, then the output would be closer to 1. The bigger the positive difference between these 2 things, the closer to 1 the output of the function here is going to be. And then this rest of this function here is just the cross entropy that we saw was how you try and push up things towards 1 if they should be 1, like in the case for classification. So in the typical case where you have a classification problem, you don't have difference between rewards in here, you have the probability of the correct class. That's the thing you want to push towards 1. So, sorry, instead of all of this sigmoid, you have the probability of the correct class, and this negative log, it goes down towards 0 as that probability goes towards 1. So the loss becomes 0 as the probability you want to be very confident in goes towards 1. And the negative log goes to infinity as it goes towards 0. So we can use the output of this difference, the sigmoid of the difference between the rewards as the input to the cross entropy loss function, okay? There's probably 10 questions there, so which part should I explain first? Let it sink in for a second, and then call it out. What does the sigmoid do? The sigmoid just let this load. Okay, so the sigmoid is a function which looks like, not like that. It looks like that. Between 0 and 1, centered at 0, it goes up towards 1 as the input gets further positive, right? So this is this sigmoid function. It's useful when you want something, when you want to turn something into a probability, like we did for our classification models, right? Classification models, they basically output a real number, which can be anywhere on this number line, put them through a sigmoid, and then they become a probability between 0 and 1, basically. So in our case, this axis here represents the difference between the rewards. Or more specifically, difference between, what it really represents is how much larger is the reward for the preferred response. That's what this represents. That's what goes into this sigmoid here. So if we do that, then this whole thing over here if we do that, then all of this section, sorry? Yeah, it'll tend more towards 1. The larger that difference between, well, the larger the reward for the preferred responses. That's right. Okay, so then let's just, again, just make sure we're really clear on this loss function. What happens to it then? There's a lot going on over here. We'll get to that in a second. But firstly, this log. What does this log do? Or what does this negative log do, firstly? Well, it looks like this. So if I draw again the graph, I can do better than that. Okay. All right. Yeah, so if we have this graph, which is the, let's call it Z. So it's going to be some score Z. And I want to know, what does the log of that graph look like? Or let's say the negative log of that graph. Well, it looks like this. Oh dear. It looks like this. And it crosses the axis at 1. This is obviously 0. And so as the input to this negative log of Z gets closer to 1, it goes down towards 0. So if you have an input which you want to be closer to 1, then you should try and minimize the negative log of it. If you minimize that, it means you're pushing that input closer to 1, which is where you want it. And as it gets further and further away from 1, close towards 0, if I have a very low confidence in a classification probability, or in our case, if our less preferred score response is has a much higher reward, then your input's going to be over here, and your loss is going to be over here. So that's the next step. We're breaking it down bit by bit, right? This should start to look more and more friendly. The only part remaining is this over here, which is basically just saying, take the average by sampling from the expected values that you get from your data set. But this average here has a funny denominator. Does anybody know what that means? I don't want to give it away. K choose 2. Yeah, you all know what it means. Exactly, yeah. K choose 2. What is that? That's how we say it. K choose 2. Exactly. How many ways you can choose 2 items from K? What do you think that represents in our case? Exactly. Yeah, you choose 2 responses to compare out of the k which a labeler has ranked. So basically, we're just averaging over the batch of examples from one task. So given all the possible pairs for one task, which would be the most preferable response and the least preferable response, most preferable and the somewhat preferable and the least preferable, they're all the pairs that you can have. You just want to average over them. So in our case, this is a 3. So that loss function should make sense right there. We'll give it just a minute. Take a look over that, make sure you understand it, then we'll code it up, and then we can finish up the data set. This E, it's an expectation. So it's like it's basically saying if you sampled from the data set, you would get those. You'd get these different X, Y, W, and YL values, and you just put them in here. So it's basically saying if I were to pick random examples from my data set, score them, compare them, and then average them, that would be my loss. That's what it says there. Cool. Good job breaking it down. Thank you for your help. It looks very hard to start. They all do. You can always break them down this way. So I didn't have time to write this one, so that's helpful. Yeah, it comes from Pascal. How many ways? Any questions about that? Yeah, so we don't use every process we only use the pairs which are ordered in a way that makes sense. So this one will always be the flip response but the order matters in this last one. Because yes, we want to minimize this thing. And so we want to minimize having a function comparing the difference between the third and the last. This is inherent. Because it's not, maybe one thing is like, it's not every order permutation, it's every like permutation. So if we have sort of the 3 different options, we choose 2, and choose 2 things from those 3. And in every single one of those, we pair once about. So. All right, so let's roll through and let's just jump back for 1 second again. Right, what we're trying to do, we're trying to train this reward model. To train the reward model, we need to have some objective which we want to minimize or which we want to minimize here. We're talking about the loss. If we want to minimize this loss, this thing computes basically is the preferred score higher than the less preferred score. So what we're going to have to do is basically for every time I want to make an optimization step, I'm going to have to compute 2 different scores and take them away from each other, pass them through this loss function. So this is not like a standard loss function, so we'll need to implement that ourselves. So I'm going to do that down here, but I want you guys to talk me through it so we can practice. So feel free to look back at your equation, and I'll probably need to as well. But how do we go about doing that? I want to have a function. I'm going to call it def loss function. it's going to take in the preferred reward, and it's going to take in the alternate reward. So what goes inside that function? How do I compute that thing? Key skill, right? Turn the math into the code. Start with the easy parts. Take the difference, absolutely. Great stuff, yeah. So I want to do preferred reward minus the alternate reward. That's the difference. Notice that the order you pass the parameters into this function matter, right? Because this thing, we want this to be positive. If I mess up that order, then I'll be optimizing the opposite thing. I'll be trying to say, hey, score the worst response better. So the order matters here, both the order of parameters and the order of that subtraction. This thing, we want to be positive. When it goes through the sigmoid, we want it to be close to 1. So that's really the next step, isn't it? How do I do the sigmoid? Torch.sigmoid, absolutely. Yep, torch.sigmoid. Do you want to do the next part too? How do I do that? Torch dot, yeah, what do you think? Yes, got you. I thought I was going to get you and you were going to say average, but yes. Torch.mean. Okay, torch.mean over that thing. Is that everything we need? No, we've missed something out. We've missed out torch.log. Yeah, exactly. Torch.log. So take the log of that. However, we don't want to minimize the log. The log would look like that. We don't want that. We want to minimize something else. We want to minimize the negative log. Sorry, the log would look like that. We want to minimize the negative log. So I actually need this whole thing to be negative. Then I think that's it, right? Is there anything else I'm missing there? No, it looks good. That looks good to my my model answer. So I'll just return that thing, okay? And then down here, I've got the full thing implemented. I'm giving it 2 examples where I've got these scalars, which I want to compare. And if I run that, it gives you, as you can see, a scalar value. Okay, that's important. This is the scalar value. We can only do dot backward on scalar values. So doing that here, after we get that loss, that'll allow us to update our model parameters by setting the gradients. Cool. Yes. Why have I what, sorry? Oh no, I've got it the wrong way around, haven't I? Yes, thank you. Cool, yeah, we can't get that wrong. What will be happening there? Look different for me. Because they're either side of the sigmoid, right? So if I've got one here, if I got the numbers the wrong way around, it would be equal distance in the opposite direction. So it should be there and there. The only case they'll be the same is if you've got the input, the difference is exactly 0. Yeah. Cool, great stuff. So that's the loss function working. Any questions about that? Cool. All right, so now I want to update my data set, because what I actually want to respond with is not just pairs of the prompt and the response, but it's the prompt, the preferred response, and the alternate response. So I'm going to go through my data set one by one, and I'm going to basically ask for those things in return. So I want a prompt, good response, and a bad response, and then I'll do the forward pass twice, once with the good response, once with the bad response. You get a reward for each, and then you compare those things, the loss function, minimize the loss. Sweet. So I need to update this a little bit. A simple way to do it, yeah, I mean, this is only going to work in the case where I've got these 3 exact columns. You might have cases where your labelers have ranked different numbers of things, so you might need to implement something more specific. But the way that I did it was I simply did the prompt response pairs in this very simple case. The prompt response pairs, I'm going to append to them. I'm going to append a tuple of the prompt and then the row's most preferable response, and then the row's somewhat preferable response. That's one pair, which is in the correct order. Note, this one is better than this one, and I only want to return pairs in that order. And then I want to do the same thing for the other possible permutations, which there are 2 more, because 3 choose 2 is 3. So the next one I want to return is the somewhat preferable response as the first parameter, and the least preferable response as the next. So there's another pair where they're correctly ordered. This one is better than this one. And then the last possible pair which I want to compare is, maybe I did that in a confusing order actually, most preferable and least preferable here. So most preferable, somewhat preferable, correct order. Most preferable, least preferable, correct order. Somewhat preferable, least preferable, correct order. So there's every permutation that I can do in this case to give out correctly ordered pairs, essentially. And when I have this final prompt response pairs, it's gonna give me those 3 things. So if I run this, we should see now if I didn't mess it up. Yeah, every example in the data set, which I'm iterating through, gives me these 3 different things. It gives me the prompt, it gives me a response, which is apparently preferred in these rankings, and then another alternate response as well, okay? Cool. So I'll give you guys a challenge. Do 5 minutes. See if you can implement the general case, right? Without using these keys explicitly. How would you do this in the general case? Imagine I had more columns. Imagine the columns are still in the right order, but they're, you know, some examples have got 5, some examples have got 3. How would you do that?
Okay, I guess you just keep it. because you can't. Then if the columns are ordered, well,
Okay, let's do this. Anybody crack the general case? Sorry? What do you think rough idea is? We don't have to implement it. Mhm.
Then like you allocate the maximum number to the most important number. So like you just go with the number, something like max minus one. It's relatively.
Yeah.
There you go.
Yeah. So something like that. Yeah. Yeah, we don't have to go into it now, but yeah, basically, you know, if you iterate through them, you can say, okay, for this one, it should be paired with this one and the next one, well, all of the next ones. For the next one, it should be paired with all of those forward. And you could probably do that with a triangular matrix if you put it in pandas still. So if it was still a data frame, you could index the data frame with like a triangular matrix, and that would basically show you which ones should the others be paired with. And then you could loop through that efficiently. Something like that. Maybe I'll do it later and I'll send you guys the result. So now we've got those three things in our data set. How do I implement the data set? This should be familiar now, but again, it is a key skill for taking your own data into deep learning. So what does the reward data set need, given that it's a torch.utils.data.dataset? Needs a few methods. What do you think? Sorry? Sorry, what was that? Yeah, it needs a constructor. So in Python, how do I define that? Thank you. What do you think goes in the constructor? Hint, hint. Yeah, so let's create the response pairs and maybe call that like self.data or something like that. And then once I've got that, those pairs of data, I guess that's pretty much it, right? Nothing else in the initializer. What else does the dataset need? Dataset needs two important things. What do you think? At the front. It needs the length. Yep, exactly. So len like that. How would I do that in this case? What should I return, sorry? Doesn't have an attribute called response pairs. Yep, self.data. Yeah. You're on the right lines. Yeah, just I didn't call it response pairs, called it self.data. Fantastic. All right. My friend, can you do the next one as well? What's the other thing it needs? Get item, exactly. What's the magic method there? That's right. Fantastic. So that defines behavior for when I index this thing. What is it taken as parameters in the middle, in the jumper with the water bottle? You got it? Okay, the Hammersley's, you got it? Yeah. Thank you. Yeah, you got it. Come on. So yeah, self and index. Because I'm talking about the behavior for square brackets. So every time I put square brackets, I got to put an index in them. Fantastic. Do you want to do the inside as well? How do I get an item from this data set? No? Okay, cool. Pass to Richard. Self.data. Yep. Brackets IDX. Yeah, so what is each of these indexes, right? It's just one of these tuples. So that's fine. Yeah, so I can return that tuple. Currently, if I try and index it though, let's say dataset equals reward dataset. The random number. Let's see what comes out. Second. All right, let's see what comes out. Nothing. Even if I print it like that. Okay, print none. What's happened here? Something's gone wrong. Sorry? Exactly. Yeah. Very very innocent mistake, but the kind of thing that might stump a whole room of very smart people when it comes to the practical. So there, you just forgot to return it, right? So it's useful to catch those little kind of mistakes which always come up, no matter how long you've been doing this. So sweet, that's the data set. Now if I iterate through it, I'm going to get back, or if I index from it, I'm going to get back these tuples of prompt, preferred response, alternate response. And that is what I need to train this model. So having done that, the next thing we want to move on to is basically creating this model, okay? I'm going to use GPT-2 as a backbone again. So starting off from this, we'll dive into this model, okay? So how do I build a model which takes in a arbitrary length sequence of tokens, predicts a scalar value from it? Where do I start with that? Challenge yourself by not looking at the next cell with the answers, or otherwise, if you need to, get some inspiration from the next cell, but then you got to explain it to me, and that might be even harder. But so roughly, like, what am I going to need here? We can start off with the very basic bits. David, you got an idea? GPT-2 model. So that's what I've got. So that is going to get me a GPT-2 model. However, this GPT-2 model doesn't predict a scalar value. What comes out the other end if I initialize this model? A prediction from the prompt. Yeah, if I've got a prompt of 50 tokens, pass it through GPT-2, what comes out the other end? what's the size of that output? If we've got 50 tokens go in, yeah, but it's 50 of them, right? So if I put in 50 inputs into the transformer, it gives you 50 outputs. The size will be 50 of 50, which is sequence length, by embedding size, which is, I can't remember what it is in this. We'll take a look in a second. So this model overall, this is not going to be the whole model. In fact, we're going to have to wrap a lot of stuff around this, right? This is going to be the backbone of our reward model. So the first thing that happens when something goes through the reward model is it will go through GPT-2 and we get out those sequence length of embeddings. And we're going to have to take one of them, we'll take the last one, and apply a regression head to it. So that's overall what we want to do. So this is not going to be the whole model, but this is going to be a part of the model. So to take it back a step, how do I define like just a PyTorch model in general? Lily, can you help me? How do I define a PyTorch model? Pass to a friend. You can point to someone. Constantine, can you help me? Come on, how do I define a model? Let's say I want to create, anything. Friend next to him. Class. Fantastic. You're great. Class. So class followed by what? The class name. What do we want to call it in this case? I like that. Yep. Good. This is getting good. Let's go. So reward model. What does it take in? You can do this one. Torch.nn.module. What does that do? So this is the parent class of our reward model, yes. And what does it mean that it's in these brackets in Python? Pass a friend?
It inherits from it.
It inherits from it. What does that mean?
That's one of the functionality of the model class.
Exactly, yes. So any instance of this class is going to have all of the same methods and attributes of this class. Cool. Can anybody tell me any of those methods which we've used so far, which might come in handy later? What do we use in the optimizer? Sorry? Dot step is a method of the optimizer, but dot backward is a method of a tensor. But between those, we need, what do we want to optimize? The parameters, yes. So is there a method that comes from torch.nn.module which I can use to get the parameters to give to the optimizer, perhaps? Model.parameters, yeah, exactly. So this has a method called parameters in. When I define my optimizer, I can do model.parameters. It'll give me all those parameters. Great. So first thing in any class we saw, define the initializer as long as it needs it. It takes in self. To make sure that all of this gets set up correctly, what do I need to put on this line? Super. Super, thank you guys. A lot, you got it there. Harder question, what does super do? What does it give you? What is this thing after I've called it? Accesses the methods and the attributes of the parent class. Yeah, so what do you mean it accesses them?
That means that you can use them to implement functionality.
Yeah, so it makes them easy to access by using the dot operator, right? So this thing basically is some Python object. It has methods and attributes, which are all of the methods and all the attributes of that parent class. That's what super does. So the one I want to call is the initializer of the parent class. You need to do that when you have a PyTorch model which inherits from module. Fantastic. Now here, this is typically where we define the layers, right? So one of these layers is going to be the GPT-2 model. I'm going to call it self.backbone. It's going to be like the main kind of backbone of the model, and we're going to both fine tune that and do something specific on top of it. So to really initialize that pre-trained, how do I do it? Anybody remember? It's not like this. That's not going to give me the pre-trained model. Dot from pre-trained, yeah, as well. Don't feel scared to look at the docs as well. I'll probably need to in a second. Dot from pre-trained, and what goes in the parameter? GPT-2, exactly. The name of the model. GPT-2, like that. Fantastic. So we've got that transformer model, and out of it, we're going to get a bunch of different vectors, sequence length by embedding size. And what we're going to do is as I showed you, can kind of make predictions to fine tune a transformer by just taking one of those representations and applying classification head or a regression head onto it. So to do that, I'll need to define my regression head. What is that? It's a class we've used many times. I've used it to define my forward layers of a neural network, to define what comes out of a classifier, what comes out of a regression model. A linear layer, yeah. How do I implement that? Nice. Fantastic. Yeah, torch.nn.linear. To do that, I'll need to import torch. And I already had it from earlier cell, didn't I? But what are the parameters? The embedding size. Sorry, what was the second one?
The second one to start with the embedding.
Sorry, I can't hear you.
You're outputting one.
One, yeah, exactly. So one output. Why is it one?
Because that's your actual.
Yeah, we just have one target. This thing needs to output one value. It's the reward, exactly. It's not a logit in this case because it's not going to be used for to go into a probability. But yeah, you're exactly right with those sizes. Embedding size, what is it? Can I get it from this thing? I'm not sure. Maybe I'll just look down here. It's 768, okay. But I could probably get it from there. Points if anybody can find out how to get it from the model. So this backbone, when I give it a sequence of t different IDs, it's going to give me a t by 768 dimensional output. Awesome. So that should be everything I need to have access to when I do like the forward pass, for example, which is the next thing I got to implement. Now, recap question. When I implement a model like this, what function does this line call? What method of the model does this line call? It calls forward. Why? It's defined the parent class. Exactly. Yeah, that's another thing that torch.nn.module does. Usually, if you want to implement how anything is called, you need to implement its call method. And whatever you do in there is what will happen when you call an instance of that class. But under the hood, this class has something like this in. So when you call it, it calls self.forward. All right, back to here. So what is the forward pass for this reward model? What happens? The clues are all up here. I've taken self, and let's say it takes in, as I showed earlier, it takes in the prompt and the response. And at the end of the day, it's going to return a reward. What happens in here? I wish you all had name badges on. Nick, what do you reckon happens? Nick's not having it today. No, okay, cool. What's your name? You're great today. Alona, was it? What do you think's happening? What goes in here? Okay. All right, pass to a friend. You can point to somebody. Payson, what's happening here?
Well,
yeah, we need a tokenizer somewhere. That's probably something I've forgotten from the initializer. So I got this. How do I get that?
Can you open it?
Yeah, let's do self.tokenizer equals that tokenizer. Where do I get it from?
Is it from pre-training?
Dot from pre-trained as well. Yeah. So it's not like it has parameters like a model has parameters, but it has that that known index mapping to token, which is how GPT-2 was trained. And obviously the numbers, the parameters inside GPT-2, especially in the embedding layer, they correspond to a particular index. So you need to get it from pre-trained if you want it to act in the same way. Fantastic. Thank you. Great stuff. Cool. So how do I use that in here? What do you reckon? Pass to a friend.
Okay.
Yeah. How do I do that? Yeah. Yes, exactly. So we want to basically somehow get like the entire input, I think. Entire input is going to be something like, yeah, start of sequence token plus the prompt plus the response plus the end of sequence token, like that. And I believe, I'll just skip ahead for a second. Yeah. So this is what they look like for GPT-2. Start of text and end of text. They look like that. But I think even better, you can get tokenizer dot. Is it going to show up there? Thank you. Self.tokenizer dot. I know we'll come to that in a second. So we'll just add the prompt and the response for the moment. And let's just get the rough outline. So what happens with that entire input, Richard? What's the next step? Yeah, we need to tokenize all of that. Self.tokenizer, self.tokenizer, how do I pass it to it? Well, one way we looked at yesterday was if you just call it on the entire text, then this thing is going to return you not just like a list of the IDs, but it's going to give you some, I never know what to call it. Probably like, yeah, context dict, I think is what I used yesterday. It's basically like a dictionary of a lot of things that are useful for the context. It has a list of the IDs, but it also has the attention mask. And that can be useful in a lot of contexts. So here, my entire text should be my entire input. And the other way that I can get the tokens as I need would be just to do .encode. And that gives you the list of IDs which come out the other end. So token IDs is equal to that. And then given the token IDs, what's the next step? Yudong, what do you reckon? No. Yudong? What's the next step? Got the token IDs. Phone a friend. What do you reckon? So I've already done that and I've mixed it up to make it an extra challenge for you guys. But yeah, so I've already got the token IDs here. These are the input IDs. What do I do with them? I want to do the forward pass of yeah, which is the backbone, right? So I want to basically call my backbone on my token IDs, something like that, okay? We're probably missing a lot of details here. We'll come back and do a wipe over it, but let's just kind of get to the heart of it. Yeah, one thing I'm actually unsure about is whether we need the attention mask here. Because if you think about it, we're only going to use the last token. And so we're only going to use the last output. So I don't know if we need the attention mask on it. But if I did want the attention mask, we would get it from calling the tokenizer like that. So I'm going to try it without. I might be missing something very obvious, so we'll come back to that later. But if you think about it, the representation that this decoder, GPT-2, needs to build, it doesn't need to hide any of the information from the last token. We're going to take the last output, and we're going to use that, hoping that it contains all of the information so far. We're going to use that representation to pass through a regression head, which will combine them all into a number. All right, good, sweet. So, given that, I get the GPT-2 output. GPT-2 output is equal to that thing. And let's just print that to start with and see if we've made any mistakes so far. All right, so I've got create the model, call the model on some data. Let's get an example from my data set like this. All right, so I'm going to pass this example through the model and see what comes out the other end. Is that going to work? No, because this forward method doesn't take in what my data set currently returns. It should take in the preferred response and the alternate response. Okay, so the forward method should take in 3 arguments, and of course it's going to pass in self under the hood as it does that. So is this going to work? Calling that model on the example, which has come from the data set. Let's have a look. It says no module name transformers. I gotta install it. Pivot install transformers. Install Hugging Face with all of the large language models and all other nice utilities in there. Once that's done, I should be able to try running this again. Run this again. I think I'm going to get an error in the trying to call the forward pass because it doesn't like how many parameters I give it, unless I've introduced any errors elsewhere before then. All right, it's downloading GPT-2. And then I get an error here. It says forward missing 2 required positional arguments, preferred response, and alternate response. So the naive way to do this would be something like this. So the prompt, response, and the response to. Do not copy my variable names. I would never let myself get away with that. But just for quick purposes, I could do this. But that's kind of like a waste of a line, really. Does anybody know how to do that all in one line? Sorry? Star. Yes, you are fantastic. That's exactly right. So if I do star example, that does something else. So can you explain to me what that does, Richard? Yeah, so it breaks up the tuple, and yeah, it unpacks. Did you say the word unpacks? Is that how you say that? So it unpacks the input, and a single star will unpack any iterable, like a list or a tuple in this case, and it'll pass them into the function which you're using that star argument in one by one. So the first item in the example will go into the first positional argument, second will go into the second, third into the third. As a quick bonus, not many people are too aware of this, but if you have a dictionary and you do star, it will pass them as keyword arguments. So each dictionary key will be a keyword, the value will be the argument. In our case, we just got a tuple list. So that, I think, should work now. We should at least get past that not enough parameters issue. All right, now it says list object has no attribute size. If we look at where that's happening, it's happening here. When I try and pass in the token IDs into the backbone, what's going wrong? It says list object has no attribute size. What kind of data type has attribute size? And why would that be happening when I try and pass this in here?
tensor.
It needs to be a torch tensor, exactly. So I'll just wrap that all in torch tensor, and hopefully that'll get us to the next step. All right, I saw a nice lot of numbers there. Okay, brilliant. Here is some big output. Let's have a look what's going on there. So that's me printing the GPT.output. I'm going to print its shape. We can take a look at that. The shape is it doesn't like that. Okay, so the output is not a tensor. The output is something else. The output has some other attributes. Now, is there a way, like, because when I printed it, it printed me all the numbers, it seemed. I wonder, is there any way to print like something simpler which doesn't print all of that out? One thing you do is you can always print dir of any object. You'll see what attributes and methods it has. It's the directory for that object to kind of look up everything inside it. So inside this thing, it always contain a lot, so it can be hard, but sometimes it can give you an idea of what is in there. So for example, you can see, oh, okay, I can get the cross attentions from this. I can get the attentions. I can get the hidden states. I can get some other stuff. But I think what I want from here is actually outputs, right? Don't know if this is in order. Otherwise, could I look that up? Hugging Face, GPT-2, goes to the documentation, scroll down to the model that we're using specifically. Look at the forward pass. You can see, okay, here's the parameters. What about the return values? That's what I care about here. Right, it contains this thing, base model output with passed and cross attentions. So this thing, it has these attributes by the looks of things: last hidden state, past key values, hidden states, attentions, cross attentions. So probably what I'm looking for is the last hidden state, okay? So this is the, if I'm reading this right, yeah, this is the sequence of the hidden states at the output of the last layer of the model. So if we go back to our transformer diagram, which is somewhere over here, yeah, then this is what I'm looking at, basically. It's a thing like this. These are all the last output hidden states, because the model that I'm using is this GPT model. It's not the GPT LM head model, the language head modeling model that we looked at yesterday when we were creating the supervised fine-tuned model. This one is just the transformer blocks stacked inside. And so what I've said is that we're going to take this output, we're going to ignore the rest of these, as I showed you can do in some other cases, somewhere else. But yeah, so basically, yeah, you can ignore a lot of the outputs and just take the last one, and we'll assume, or at least we will, we'll initialize the model parameters such that, well, sorry, in the future, we will train this so that this becomes the inputs that are needed to predict the correct reward. And of course, we're going to need to fine tune this thing on our reward data set. So next thing that needs to happen is I need to basically get that. So can anybody talk me through, you know, if you had to figure this out, like how would you go from here? You've got this information. So, you know, you've got this output. It's got a thing called last hidden layers. And what do you do from there, right? Because you might find yourself in a situation like this where you know what you need to do conceptually, but how do I take it forward? I want one of you to kind of code through me, you know, tell me what to print, tell me what we should change, and we can do it. So that's, yeah, print the shape. That's a good idea. So print the shape of this thing. That thing probably is a tensor. That would be my guess. No, it has no attribute. Did I print that correctly? Yeah, I've given it the wrong attribute name firstly, so that's an issue. So lost hidden state dot shape. Let's run that. Cool. What does that tell you? What should I do now? I want to access the final output. Yeah. Why is it 2? That seems short, doesn't it? Is that just like a one particularly short prompt, or what's going on there? Yeah, I think we might have something wrong because that probably shouldn't be 2. But yes, Amelia, I want to access the last output. So how would I do that? Index the last the -1. That's exactly right. So I'm gonna just say the GPT-2 output is that. So I'll get the last hidden state from it. Then I'll get the last hidden. I don't know what I want to call this. Well, the last hidden layer outputs would be equal to GPT-2 outputs with this thing on the end. So I'm going to move that down there just so we can get it really clear. And then the last, what do I want to say? Like last sequence output is equal to the last hidden layer outputs index with a -1. So I just want to get the last one out, and I'm going to train the model to make sure that that contains all the information that I need. Now, where do I go from there? Let's print the shape of that thing. Go for it. What is this thing? So this thing is what comes out of the forward method. So it's this thing here. It's of type base model output with pass and cross attentions. So it's basically some Python object of this class, which is a class from Hugging Face, which has these different attributes. It has the last hidden state, which will give you that. It has the pass key values, all the hidden states, the attentions, and those kind of things. The last hidden state is this. Yeah. So vectors, vector representations come in, contextual vector representations come out of the transformer, and inside there's all kind of things like attention and cross attention happening. And so this output this output is very flexible because this thing can give you access to the different things if you happen to need them, which in a lot of different interesting models is exactly the case. Yeah, great question. So what do we do from here? So we've got this last sequence output. Let's print its shape. Let's see what happens. Okay, so the output is 768 dimensional. Is that all we want? You're ahead of the game. That's exactly right. We need to add another dimension, the batch dimension. I was going to say, yeah, that's the right shape, but you're exactly right. The next thing is it needs an extra batch dimension because in PyTorch, let me hear you say it. The last dimension is always the batch dimension. Exactly. That's right. Sorry, the first dimension. First dimension is always the batch dimension. So, exactly right. So how do I change this thing, which has shape 768? How do I change that so that it's shape 1 by 768? Because we just got a batch size of 1 so far. How do I change that? Dot reshape, I could do that. Last sequence output is equal to this thing dot reshape. What would I reshape it to? Sorry, I didn't see who said that. My batch size, which in this case is, and 768. Yeah, so something like that. That would work, I think. Let's see what shape it comes out as. Cool. That's good, right? That's exactly the kind of size that we want to go into our linear layer. Batch size by number of inputs. There is an easier way to do this though. Has anybody seen me use it before? I just want to add one dimension in one place. Unsqueeze, yeah, brilliant. So unsqueeze is the opposite of squeeze. So squeeze, what it does is a tensor with any dimensions of size 1, it just removes those dimensions. Unsqueeze can add in dimensions of size 1 in whatever position you give it in the argument. In our case, we want the 0th position. That is the batch dimension to have size 1. So now if we run this again, we should have the right size, 1 by 768, fantastic. What happens next? We're getting very close now. I've used the backbone to get the right sized output representation. What do I need it for? Where does it go next? It goes into the regression head. Yeah, exactly. How do I do that? Sorry, what was that? Yep, exactly. So put that thing in there, and that should get me what? What comes out of there? The reward. Yeah, that's the reward. Like that. So now, let's see if this works from end to end.
Why are you passing
Why am I passing in multiple responses into the forward? Yeah, I probably shouldn't be doing that, should I? You're right. Because the diagram I showed earlier, I said that the reward model takes in a prompt and a response and returns a single reward. So yeah, you're absolutely right. I think I should only be passing in one. It's a mistake there. So yeah, I don't want to do that actually. Thank you for that. So prompt and response, that's what I've got. I can concatenate them all together for that prompt response pair, produce a reward, exactly. So let's see what comes out the other end if this works. Now it says it doesn't take enough parameters, so I will actually need to unpack that. Cool. Then I pass in the prompt and the preferred response. Could pass in either. In fact, why don't I pass in both? Thank you. Which ones? Yeah, cheers. Nice. Look good. Thank you for catching my bugs. Let's run it, see what happens. All right, these things, they apparently cannot be multiplied together. They are the wrong shape. So what's happening here? Sorry, what? Ah, yes. Yes, there I've said S786. Where have I introduced that? There it is. So it's 768, brilliant. This is so helpful having team people to bug fix as we go. All right, are we gonna get the reward? Are we gonna get the reward out right now? Green tick, yes sir, there you go. 2 rewards, 2 scalar values, 2 prompts, sorry, 1 prompt, 2 responses. Different ones give different rewards. This is the initialization of what GPT-2, sorry, GPT-2 and a totally random regression head, untrained, not going to give you anything good right now. This is what it predicts. So the next step is to train that initialized random regression head and probably the parameters of GPT-2 as well. So updating those. Fantastic. So any questions about that? Firstly, that was the forward pass implemented there. So this is one thing I'm actually not sure about the detail of. So I'm not sure I'm not particularly sure why you would use a encoder instead of a decoder instead of an encoder, or if there's any difference if you don't use the attention head in this implementation. The attention mask, because I didn't pass in the attention mask to the model, so I haven't actually hidden what it's paying attention to. And so I think what we've got here is the parameters of GPT-2 being used basically as a decoder, as an encoder, not a decoder. I'll have to check that though. But it's arbitrary. I could have taken the first one as well, because I haven't passed in the attention mask here. And all of the outputs can pay attention to all of the inputs.
So they can pay attention.
Yes, they do. Yeah. That's right, yeah. Every layer of the transformer can pay attention to any of the inputs in the layer before, unless you have an attention mask covering it up. In this case, we didn't use the attention mask, so we're looking at all of the inputs into this so far. Sorry? Sorry, which way? Yeah, to me, it makes sense that like we don't need to cover anything up because, you know, in this case, we don't want to cover up the previous tokens. We want all the information from them. Even if we had put the attention mask in, the last token would have paid attention to all of the others in sequence anyway. So I don't even think it matters the output values in this implementation as well. Yeah. David?
Is it normal to use the same model as the backbone that we're going to train?
Yeah, great question. Is it normal to use the same model as the backbone that you're going to be training? So note here that this reward model has a GPT-2 model backbone, and my supervised fine-tune model also has a GPT-2 backbone. That's what we're saying, right? Yeah. Yes, it is. Yes, it is pretty common. Yeah. In the Instruct GPT paper, which is the research that ChatGPT builds on, that's exactly what they've done. So they've used for step 1, 2, and 3 supervised fine tuning, reward model, and the overall final model. They're all GPT-2 variants. Cool, great stuff, Lily.
We use the pre-trained GPT-2.
Mm-hmm.
It's not the fine-tuned one from yesterday.
Yeah, good distinction to make there. So here I'm using the off-the-shelf pre-trained GPT-2. This is not the one that we used yesterday, and that's because we're talking about a different model now. We've got the supervised fine-tuned model. That's the one which we fine-tuned for language modeling. Now, this one is totally different. It's totally brand new, and it's used for modeling the reward. Later, we're going to use this reward model to give feedback to the supervised fine-tuned model by giving it scores for how good the supervised fine-tuned model's responses are.
So what is important today is to train the hat, the regression hat.
Mm-hmm.
And you said before that in the training process, the regression hat is trained. It's our manual.
Mm-hmm.
And also the parameters of the GPT-2 may have changed.
Mm-hmm.
So you don't mind if it is changed. You just pick the regression path, the reward model out of this is the whole backbone, the whole reward model. So we don't care if the GPT-2 parameters.
Okay, right, yeah. So I see there may be some confusion there. So to walk through what we're going to be doing. Firstly, to answer the question of, does it matter that the GPT-2 parameters, which are pretty good because they're GPT-2, does it matter that they change? No, it doesn't, because they're being fine-tuned to be better on our task. You might want to, so what we're doing here is we're just training the whole thing from end to end. You might want to do something like weight freezing, which we talked about a few weeks ago, which is where you say, actually, I want to keep the backbone totally fixed. I'm just gonna say it knows what it knows, and I'm assuming that's really good for the task, and I'll just tune the model head. That's one option, or you could use a discriminated learning rate where you update your model head quickly and you update the model, the backbone, but slowly. So just to answer the question there and draw a line in the sand, it doesn't matter that the backbone parameters change, and you might use some of those techniques to change how much they change. That's one thing. The second thing is that I am not, once I train this reward model, I am not going to separate out the backbone and the regression to do something different with them. I'm just going to keep this all as one thing. So this reward model is going to is going to stay as one whole block. I think what it sounded like, and maybe I'd made it sound like, was that we were going to take this regression head off and use it on our supervised fine-tuned model. That is not what we are going to do. That's not what we're going to do.
So the reward model is the whole part actually.
Yeah, the reward model is the backbone and the regression head all at once. And what that means is that the backbone as a transformer can take in an arbitrary length sequence, any response of any size, and it's going to put them all out. It's going to take contextualized embeddings of those inputs, and it's going to then turn that into a single number, which is the reward at the end of the day, the reward for how good that response is to that prompt. Now the supervised fine-tuned model, that's only going to take in the prompt, right? It's going to take in the prompt to give you a response. Again, same architecture, but it's trained for a different purpose. The supervised fine-tuned model trained to give you the response. The reward model trained to take in the response, take in the response as well as the prompt and give you a number.
So when you use the reward model in step 3,
Mhm.
you use all the like the backbone. and
Exactly.
the-
Yeah, we're going to pass it through this forward method again.
Oh,
Yeah.
okay.
Yeah. Does that make sense?
Yeah.
Cool. Great question. Really great. Nice. So now we've got these scalar values out. The question is, how do we train this? So I want to jump towards that. There's another implementation of the thing here. I've used the start of sequence and end of sequence tokens, and there may be some other things I've done slightly differently. It'll be great if you want to compare them or just see if I've left anything out. So please check that out. But the final thing is the training loop. So let's see if we can get this to train. I'm going to start up TensorBoard firstly, so we can see how the training's going. And then I got to implement this. This train method. So I'm going to take all of this as a starting point, and then we can walk through it together before we wrap up. So the training loop looks pretty usual up to this point. So train, I create the data set, I create the optimizer. These are some of the parameters that we use in the Instruct GPT paper, so I've stuck with those. I set up my logging by initializing something that can write to TensorBoard and a batch, and initializing the batch index to 0. I'm going to go through the data set a number of times. That is how many epochs I want. And then I'm going to go through each batch in the data set. So what happens inside here? Peyton, you want to kick us off? You can start anywhere. Don't feel like you got to do it in order. So we've got the data coming out of the data set here. That's what's in the batch. So what might I want to do with that batch?
Take out the
Yep, want to unpack it, that's for sure. So prompt, preferred response, and then the alternate response. That's what's equal to the batch. Fantastic. What do I do from there? Run it through the model. Yeah. So how do I do that? Yeah, I didn't initialize my model, did I actually? So let me just get that model. So I'll initialize a model in here. I'd usually pass that in as a parameter, but we'll just do it all inside the loop here. So pass what through the model?
your prompt and the response.
Yes. Like this?
Oh, no.
Exactly, yeah. And this is where the training loop is going to start to look a little different, right? So this one is going to be the preferred reward. But then I'm also going to get the alternate, oh, not that. I'm going to get the alternate response reward. These two things I'm going to need in the next step. They'll go through the backbone, they go through the... All right, great. So just separating out there. Can anybody do the next step? Friend here had a hand up. Yes, sir. Like this? Yes, I've got to have an order, exactly. So they need to go preferred response first, alternate response second. That's the loss. What do I do with that? Friends at the front. Loss dot backward, straight to it. All right, cool. Loss dot backward. What does that do? Calculates the gradients. Where does it put them? Where does it put them? Where does it store the gradients? Sorry? Not in the optimizer. The optimizer will use them in the next step, but that's not where they get stored. Where do they get stored? Can your neighbors help at the front? Where does loss dot backward put the gradients? Loss dot backward calculates the loss, the rate of change of the loss with respect to all the model parameters. That is the gradient of the loss with respect to the parameters. So where do these parameters end up? This is a side question. Anybody help out from the middle? Not in the, well, yes, but in the parameters specifically what we're talking about, right? So in all of the parameters which contribute to the loss, which may not just be from the model, maybe from, maybe from some calculations you've done with the model output, something like that. Yeah. So cool. So that's where they go. Loss dot backward. What do I do once I've done the loss dot backward? Getting very close now. I've got the gradient stored. Nick, what's next? What dot step? What is it that we need to take steps? The optimizer, exactly. Yeah, I need to take an optimization step. I'm mixing up my British and English here, so I just need to check whether it's a Z or a Z. Z or an S. Cool. So optimizer dot step, that should make a step. And then I'm all good, right? And then I can just continue to take steps and do that same thing on a loop. I have to zero it, yes. I'm really trying to catch you guys out. You're too quick. So I got a zero, what? What have I got a zero? Zero the gradients, yes. Why is that? Exactly, yeah, that's a spot on answer, the one I've given many times when we're talking through this. So that should be the loop. Haven't missed anything else. This is not a trick question, I'm genuinely asking now. Haven't missed anything else there, or does that look good? It looks alright, I think. Good idea. Yeah, I should probably do some logging. So let's do writer.add scalar loss slash train, and we'll pass in the loss dot item, which I can call that method on any scalar tensor to get the value, and we'll pass in the batch index here, and then we'll increment the batch index. All right, shall I run it? I'm about to do it. Here we go. All right, is it going to run? Yes, I've just defined the function. Now I need to actually call it. All right, there we go. Run this, see what happens. This thing is not defined. It says ChatGPT GPT-2 reward model. That's not what it's called. Where did I get that from then? Oh, that was from my second implementation. Okay, I'll run that. And then we'll run this. And we'll see what happens. Error. Unsupported operand types for subtraction between string and string. What's happening there? Well, there's only one place where subtraction is happening. That's in the loss function. What's wrong with the loss function? It's probably not with the loss function, is it? It's probably with the with what these values are actually. So let's go back down to the and take a look. Yeah, so I've not passed in the reward, I've passed in the actual string. So passing the reward. Run that. What happens? Let's have a look. Too soon. Your session crashed, automatically restarting. So I apparently used up all the RAM. Well, at least now it's cleared the RAM. So let's do runtime, run everything before, which includes the cell.
Harry?
Yep.
While we're waiting for this to load, have you ever run optimizers that get, or why isn't zero brand built into the stack?
Good question. Yeah, good question. Yeah. So and at the end of this, I've got a challenge, which is, oh no, that was yesterday. Okay, so from yesterday's notebook, there's a challenge, which is basically for you guys to implement what I've called proxy batching, and that might be the first use case of where you do want the gradients to accumulate. So what is that? That's where, because these models are really big and the data and sequences can be really long, you might have it that you can actually only fit one sequence on your device at a time. So that means you can't process multiple batches at once. But we want to process multiple batches at once, right? Because the idea is that if I have more items in the batch, then the gradient updates are averaged over those items, so they should be more reliable. Because if I got more samples from the data set, then I should have a more reliable idea of how the model should perform. And so if I can only fit one example in each batch, then what you could do instead to proxy the batching is to basically say, well, I will do a forward pass for subsequent examples, let the gradients add up, and then maybe after I've done batch size of them, I'll do optimizer.step and then optimizer.zeroGrad. So that way you could kind of fake the fact that you've got batches and hopefully get more accurate gradient updates. That's one use case. Yeah. I'll look up some more as well because I keep. Yeah. Do I know one? What? Sorry.
So maybe sometimes you want to do some of the previously,
Mm-hmm.
0.1.
Oh yeah, so momentum, that can be built into the optimizer. So that's actually built into Atom, and that's what these parameters control here actually. They basically control the exponential decay of how much the previous gradients and gradients of gradients influence it. Yeah. So but that's including the optimizer, like Atom, which is actually not named after anybody, but stands for adaptive momentum. So that's where that comes. Good question. Cool. Is this running? Did I hit another error? Oh, damn it. Must be losing faith with you guys in my spelling over these few days. All right. Let's run this. It certainly got to the end of one, and then it hit that. So let's see. This, we might not be able to get because it's going to take a while. This is a very big model, and the sequences are pretty long. So if we don't get to too good of a visualization, because I've got to cancel it and we can only look at 5 updates or whatever, then I hope this has been a clear highlight of how the process of training the reward model works, right? I think we probably missed out a lot of details. There are probably details that are not disclosed that we've missed. There are probably others which are disclosed and I've missed anyway. But I hope it's been a useful highlight for how you could train a reward model. And maybe if you had your own use case, how you could implement reinforcement learning for human feedback in your own system. So tomorrow, we will look at that reinforcement learning setup for this process, how to implement RLHF, and that should wrap up this overview of how ChatGPT works. So for now, I'm going to end perfectly on time, and I'm going to let you guys go right now. I'm gonna hang around here so like if you want to hack and work or go for anything, like I'm happy to do that. I'm not gonna rush off today, and then I'll catch you tomorrow. Tomorrow's gonna be big. It's gonna be the final summary. And I've got a bunch of stuff to give away, and including cash prize, including merchandise. So if you haven't already got some, you can get your hands on it then. And with that, I'll leave you guys to it, and we can catch them tomorrow. Hello.
The sequence is very important. Why do you want to ask questions at one dimension?
Yeah.